Am I sharing the right screen? Yes. All right. So we are going to start off with MedChem, the antiarrhythmics. So as you guys learned, the antiarrhythmics are a wide range of classes where the ultimate goal is that the action potential of the heart muscle is disrupted in some way, and we can use the different antiarrhythmic drugs to help reset the arrhythmia that is going on. So all the different drug classes have a different uh, kind of place that they go to attack different areas of the action potential, whether that's, the inflow of the sodium or potassium, the recovery phase, all those sorts of different things. So what we're going to do is we're going to break down how to identify the different antiarrhythmics into where they go. What I will do is let us just list out what those identifiers are going to be. So for class 1A, the identifier is going to be that we have some sort of big lipophilic area. And then that's going to be connected to a very basic nitrogen. When we look at class 2, well, I'll do 1B instead. When we look at class 1B, this is going to be similar, where we start with the lipophilic area. The difference is that we add the aniline with the basic nitrogen. And then finally, for class 1C, we go back to our lipophilic area. Lipophilic area. Which is they are, yeah, secondary. So this will make sense once we go through it. So the essential kind of moiety that we're going after, that we can kind of walk our way through. When we look at the class 1A, what we are, we need to move this. Oops. When we look for class 1, anything in class 1, what we are looking for is a pretty significant lipophilic area, which means at least a benzene ring. And then we're looking for a 3 or 4 carbon spacer between the nitrogen in the structure. So for example, if we look at quinidine and procanamide, as well as diisopyramide, all of these are going to fulfill our requirement of having this lipophilic area, so at least a benzene ring, where we have 3 or 4 carbon distance between the basic nitrogen. So in this case, our basic nitrogen that we care about is these guys. And what kind of nitrogen do we find in class 1A? What functional group is this? Tertiary amine. So all of your class 1A antiarrhythmics are going to have tertiary amines. And we can actually fill that in here. And we can say that we have a tertiary amine. Compare this with the compare this with class 1B, and the difference here is that we use the aniline molecule to build up our lipophilic area. And we'll throw phenytoin in here. Phenytoin's a special case. We'll talk about it in a second. So for class 1B, instead of having just a lipophilic area connected to this tertiary nitrogen, tertiary amine, the difference with them is that they all contain aniline. Aniline is where you have a benzene ring, and coming outside of the benzene ring is that nitrogen. So each in 1B has this aniline moiety except for phenytoin. Phenytoin is the only one that breaks this this rule. And we'll talk about specifically what that means for phenytoin. But in general, most of these drugs are going to follow the same sort of format. You'll notice that mexiletine is essentially the same as tokenide, where they just, instead of having this amide here, they swapped it out for the ether. So let's talk about this. Here we have the amide moiety. What does swapping it out for an ether do? How is this going to change the molecule? Decrease metabolism. Exactly. So the ether that's in mexiletine is going to decrease metabolism because we're not going to be able to break apart the amide like with amidase. So does that mean that mexiletine is going to have a higher or lower half-life compared to tocamide? Should be higher. Exactly. And in fact, when we look at toconide, it has a half-life of around 8 to 12 hours, whereas mexiletine has a half-life of about 16 to 20. So not too bad. What this means is that when you look at mexiletine, does it follow the pattern? Kind of. The way I like to point it out is that it is just a modified version of tokenide, which I think helps explain why it's part of this group. When we look at when we look at any let's compare tokenide and mexiletine, then we'll go back and we'll talk about no, I want to bring up 1C just so we can all compare them. So let's grab the next class, 1C. flecainide and propafenone. And when we look at this class, what we see is that we have the same lipophilic area that we care about. We have that spacer, right? The 3 or 4 carbons. But instead of having a tertiary amine, what we have in class 1C is a secondary amine. And that's the main differences between all of these drugs when you're talking about, you know, what makes one drug a class 1A, 1B, 1C. When we look at what's going on, we can say that in class 1A, their duration of action is longer. For class 1B, their duration of action is shorter. And for class 1C, their duration of action is unchanged. So comparing 1A and 1B, why is 1B have such a shorter duration of action versus their brothers and sisters in 1A or 1B or 1C? Exactly. Remember, duration of action is a function of metabolism. So in the 1B class, they all have this easily hydrolyzable amidase, amide that could be metabolized by amidase. And so this aniline moiety is going to be super, super easy to break down, which is why on average, the 1B molecules have a very, very short duration of action. If we look at drugs like procainamide, they also have this amide functional group in them. But what's different between the amide that's in procainamide versus toconide? What's the main difference? Exactly. Because the nitrogen is facing away from the benzene ring, we actually decrease its ability to be metabolized. So in other words, having the nitrogen be on the opposite side from the benzene ring makes it less likely to be attacked and metabolized. It all has to do with how the partial charges kind of work out. If you were to look at the nucleophilic ability, the electrophilic ability. Yeah. We can go into SN1 and 2 if we want. Phenytoin is a special case. Phenytoin does not have a aniline moiety like we see in lidocaine or toconide, and it's not a modified structure like in mexiletine. But what it does have going for it is that it has this very acidic oxygen here. Sorry, I drew it in the wrong place. Essentially what this is that we have oxygen. Oh no. Am I crazy? I am crazy. Yeah, it's not that oxygen. I'm talking about the nitrogen. It is this guy. What's funky about this nitrogen specifically is that it is acidic. So what I want you to remember specifically about phenytoin is that it's the only acidic sodium channel blocker. Every other sodium channel blocker is basic. All of their nitrogens, whether it's the tertiary amine, whether it's the primary amine, or this other tertiary amine, or the secondary amine that's in the class 1C, all of them are basic except for phenytoin. All right. Let's talk about some other important factors here. One of the things that can end up happening with ethers is that they can be split apart. So through simple hydrolysis, what can happen is that this bond can be cut in half. So for propafenone, what can happen is that enzymes can come in and cut this ether, which would metabolize the drug and destroy its property. What do we think the purpose of these fluorines are? What would that do to the metabolism of the ether comparatively? Not necessarily because of steric hindrance. Fluorine is a very, very small atom, but what this is doing is decreasing metabolism by through electron induction. So essentially what it is that these fluorines are slurping electrons away from the oxygen, making it less likely to be attacked. So instead of it being this nice site for it to undergo metabolism, the fluorines are stealing those electrons through the inductive effect. So whenever you see fluorines on a molecule, I want you to think less metabolism. All right. Other things that we should talk about are drugs that have good bioavailability. So whenever you see a nitrogen is very easily able to pick up a hydrogen and become positive, especially when that nitrogen already has a hydrogen bond already. So when we look at this, all these different groups of molecules, tokenide has very, very good bioavailability. Bioavailability? Sorry, absorption. My bad. No. Am I crazy? Da, da, da. Sorry, I said that wrong in my head. Because this nitrogen can be what's it called? Can gain a charge. This would lower the absorption of tokenide, right? So whenever we look at these different drugs, the compared to a molecule that didn't have these basic nitrogens, which is all of the drugs in class 1, they all have a bit of a hard time getting into the body because they all can pick up a hydrogen and they can all create that positive charge, which makes it tough for absorption. All right. Last, great question. Exactly. Phenytoin, because it is the only acidic nitrogen here, this is going to enable phenytoin to be absorbed at a better, easier rate. So the absorption of phenytoin would be easier, but the bioavailability of phenytoin is pretty low because of those big benzene rings that allow it to be metabolized. Not good. All right. Which of these drugs would have would need to be protein bound in the blood? Which of the drugs would need to be protein bound in the blood? Um, Phenytoin is highly protein bound, but not necessarily because it's acidic. So when we think about, yeah, when we think about protein binding, plasma protein binding, the reason why a molecule would need to bind to albumin is because it is mostly nonpolar. A drug that is highly protein bound means that it has more lipophilic areas than hydrophilic. And the way that I always like to make people think of it is that we are always looking for those OH, SH, or NH bonds. So looking at these different drugs, we can see that, here in procanamide, we have lots of NH. We have two NH bonds, another NH bond. This can form a hydrogen bond under acidic circumstances. Same thing with diisopropionide. We have hydrogen bonding here. Toconide, mexilitine has this two groups here. So in terms of the ones which are highly protein bound, phenytoin is one of them, because even though we have this nice NH bond here, we still have two giant benzene rings. The other one to consider is quinidine. Even though quinidine has this OH bond, we still have two giant benzene rings, as well as a huge ring over here, witch's hat. So quinidine is also highly protein bound. And then I think there is one more. Nope. Yeah, I think that is pretty much the only two that would be highly protein bound. Does that make sense from when we look for protein bound or not? All right. All right. Class 2 antiarrhythmics is the beta blockers, which we're not going to go over because you've already been tested on it. Class 3, we are talking about the potassium channel blockers. For the most part, all of the potassium channel blockers are going to follow this format. Benzene, O, nitrogen. Unlike the sodium channel blockers, which are all about lipophilic area like benzene. And then we have a nitrogen that we worry about, right? Either a tertiary amine or a secondary amine, or we're worrying about that aniline moiety. Here, we need to see that we have the benzene ring, benzene only for the most part, then an oxygen, then a nitrogen. Bisoprolol. I'm not a huge fan of bisoprolol. All right. So let's look at the drugs that are similar to each other, and then we'll look at the exception, because there's always one exception. Butylide, dofetilide, amiodarone, and dronedarone. All right. So the first drugs we're going to look at is ibutylide and dofetilide. And here we can see that we have the benzene ring. We have the benzene ring, O, nitrogen. We have our benzene ring, O, nitrogen. Same thing over here. Benzene, O, nitrogen. And this is one of the identifying pieces, that you can use. Again, does this have really any main purpose in like real medicinal chemistry? No, but this is how one way that you can help remember what the drugs are in a class. A couple of key points that we see throughout these different drugs is, first of all, this moiety here. This is the sulfonamide. What I will tell you is that the sulfonamide is required for potassium channel activity. It has super, super, super high affinity for the potassium channel. So if you were going to make a potassium channel drug, you would not be able to choose one that does not have the sulfonamide portion with it. The other important one that we should look at, I just want to grab a example. Oops. Maybe it was in this one. If you remember way back when we talked about beta blockers, the important aspect of beta blockers was that we had the benzene ring. Yeah, the benzene ring, and we have this 3-carbon spacer between the nitrogen. And this was really, really important for the beta blocker activity. In order to prevent the ibutylide from just being another beta blocker, what it uses is this long tail. So normally, for a beta blocker to work, you need to have your oxygen, and then a couple carbons away is the nitrogen. These are the key components. Then on the para position, you need to have some sort of tail. For ibutylide and dofetilide, that would be totally, totally fine for them to have the oxygen, and then a couple carbons away is the nitrogen. In order to prevent that, they need to have this large tail on the nitrogen to stop it having beta activity. When we look at ibutylide, what is the danger of this long tail? What can happen here? What's always the danger of sticking just more and more carbons as a tail? Yeah, what this does is a long tail means aliphatic hydroxylation. So in order to stop the beta blocker activity, we need a long tail, but that's going to decrease the half-life of the drug. That's part of the reason why we have an ethyl group here, right? If it was another long tail, we just have more room for aliphatic hydroxylation. What exactly? So it's all about risk and benefit. You want less beta activity, well, you're going to have a lower half-life. What's important to know too is that ibutylide is the base drug. It was created first. And here is ibutylide. What they did is they took another half of this drug and they stuck it on as the tail. So essentially, dofetilide is what's called the dimeric form. It's just two drugs stuck together, the same drug stuck to itself. All right, let's go into the other two. Amiodarone is a kind of an interesting drug. Amiodarone has a couple of key pieces to it. The first is that we have this benzene furan. The benzene furan is an aromatic group. And specifically, what we have going on is we have hello?
We can hear you.
Could you hear the birds in the background?
Yes.
Yeah. Essentially, what's going on here in amiodarone is that we have the aromatic group of the benzfuran, and in between them is the ketone. So we have an aromatic group, a ketone, and they're pissed off about benzfuran. Let's see if you can see them up there. My boyfriend brought over his Quaker parrot, and they're pissed right now. It is the fact that you have this ketone straddled by two different aromatic groups that gives amiodarone its function. So this double aromatic ketone is what creates the affinity for the potassium channel. Can you cut it out, you two? All right. When we look at dronedarone, same sort of thing. We have two aromatic groups, and either side of the ketone is an aromatic group. So that's what makes dronedarone and amiodarone into potassium channel. Give me 1 second. The other key thing that we should look at, they're on top of the cage right now, but if I kept them in the cage, they would just scream. The other thing that we should look at in amiodarone specifically is the iodine atoms that are in it. Amiodarone mimics the endogenous molecule thyroxine. No, thyroxine, which is a component of the thyroid's functionality. And what this can lead to is issues with the thyroid. So in someone who has a thyroid problem, whether that's hypothyroidism or hyperthyroidism, either one, we should not be giving amiodarone. Amiodarone is not a good drug to be giving. You'll see also in dronedarone, they improved the functionality by creating that sulfonamide, which once again increases the affinity for the potassium channel, and they got rid of the iodine, so that way we don't have a big issue. What other major difference can you identify between amiodarone and dronedarone? There's one other big one. Exactly. So in amiodarone, we have this ethyl group, which is easily able to go through N-deethylation. So to prevent that sort of metabolism, dronedarone extends the tail into a butyl group, but we know that this can go through aliphatic hydroxylation. So in effect, you're kind of swapping out one thing for another. What I will say is that the interesting part of amiodarone. So, does anybody know what the half-life of amiodarone is? Super, super, super long. It's about 60 to 140 days. Whereas the half-life of dronedarone is about 13 to 20 hours. What do we think accounts for, which essentially means that you can take one dose of amiodarone and it will stick around your body until the end of the year, a year later, which is nuts. What do we think? Why do we think amiodarone has such a long half-life? Part of it, yeah. So what ends up happening is that those iodine molecules make it it's able to be taken up into fat cells. And so those fat cells cling on to the drug and release it slowly over time, meaning that the effective half-life of the drug is that it is super, 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 super long. So this is one of the big aspects of dronedarone, is that if we wanted to give someone a drug, if we wanted to give someone amiodarone, but we're worried about it lasting too long in them, we can go to dronedarone. Now, there are benefits to having the longer half-life, right? if grandma forgets to take her pill the next day, she's still going to be covered because she's taken a ton of it. But just kind of an important piece. Any questions about this? Is this helpful so far to go through these? Okay. All right. That's the big thing. All right. Last class is class 4 is the calcium channel blockers, which we went over before. Any questions about those drugs that we went through? All right. What does he have next? Congestive heart failure drugs? CHF? Okay. Oh, that means we get to talk about DIG. Oh, DIG. Disgusting. That's funny. All right. 2 drugs. Digoxin and digitoxin. So, digoxin is what's called a cardiac. Oh, God. Digoxin is what's called a cardiac glycoside, which is just a fun way of saying that it is a sugar-based molecule. Sugar in the chemical sense, not the delicious sugary sense. Essentially, what it is that the no, it does not taste good. Digoxin is a interesting molecule because it's using plant steroid. So unlike cholesterol, which is an animal steroid, which uses that 4 fused rings, 4 cyclohexane fused rings, what plant based molecules are doing is they're using a different way of fusing the molecules together. So in animal products, it's a trans ring fusion, whereas in a plant steroid, it's a cis ring fusion. Really, what you need to know about digoxin is that it has a very narrow therapeutic index. Super, super, super narrow. It does not take a lot of digoxin to poison someone. The important aspect to be aware in digoxin is you have the glycoside portion here, so the sugary portion, and then we have the steroid up here. This is the foxglove. So digoxin is naturally found in a plant called foxglove, which is its family name is digitalis. And it's one of the reasons why you cannot eat foxglove plants because it is they're super, super, super toxic. What do we notice about having the glycoside portion of the drug and the steroid portion of the drug? What does this mean for digoxin? Well, essentially what it is, what are you talking about? There's no OH on the steroid. Did I copy the same structure? Mm-mm. Oh, my bad. Digitoxin has uh yes, that's the structure's wrong. There should be an OH there. Well, we're going to talk about why that's important in a second. So, in anyways, the glycoside portion of the molecule is really hydrophilic, meaning that it is easily going to dissolve in water, whereas the steroid is very, very lipophilic. So what this means is that digoxin is um, easily absorbed by the body. In fact, it's absorbed by passive diffusion, which is unusual for such a large molecule, for such a large drug, because it usually you have to have some sort of active transport. But really, the important part here is that it has this dual nature to it. Normally, steroid drugs are protein bound. They're not very easily transported in the blood, but because of the glycoside, we have low protein binding. Why? Because the sugar allows for digoxin to dissolve very easily in the blood. The last part that's important to know about digoxin, the fact that in digoxin there's an OH molecule, whereas in digitoxin, it is in digitoxin, it is oh no, whoops, I put it in the wrong place. It's not there. It is right there. So in digitoxin, that position is just a hydrogen, whereas in our drug, it is a hydroxyl group. So on carbon 12, we have that OH group, and this is what makes digoxin less toxic, and what enables it to be used as a drug in congestive heart failure versus a drug that's going to completely stop your heart. All right. Any questions about dig? It's kind of the key parts to it. Okay. What's up next? Oh, PDE3s. All right. What we're going to talk about here, and before we get into that, is the positive inotropic drugs. Where digoxin helps with enabling the contraction of the heart, so that way it has a positive inotropic effect. So in other words, in heart failure, the heart muscle is weak, and so we can use a drug like digoxin to increase the force of contraction. So it's going to be pumping at a better rate. or be pumping at a better strength. Unlike digoxin, which is highly, highly toxic, these other drugs have the same thought behind them. They're all going to increase the force of contraction, which is going to decrease the heart failure, right? Remember that in heart failure, the whole piece about it is that we need the heart to work better. But because of cardiac remodeling, making the force of contraction go down, these drugs are hopefully going to be relieving that to some extent. PDEs for heart failure and those for antiplatelet effects. PDEs for antiplatelet? And nagrelide. What section was that in? Was that in NSAIDs or was it in antiplatelet? When we finish up this, I'll take a look. But we'll finish up the CHF drugs and then we'll take a look. All right. So the first class of drugs we're going to look at are the PDE3 inhibitors. What's interesting about the PDE3 inhibitors is that they follow the same format, where they're going to be an aniline, not an ant, nope, a pyridine, a mid-pyridine. So what we have going on in these two drugs, and the way that I always identify them, is that we have this pyridine moiety connected to another pyridine moiety. Are they both really pyridine? No, but it's a good way to identify them. What's interesting to know about the PDE3 inhibitors is that having a substitution on the pyridine ring this is going to increase the potency of the drug astronomically. The biggest thing is that we want electron withdrawing groups. So, for example, looking in milrinone, we have both the methyl group and this nitrile group. And so each one of these is going to increase the potency. Now, when we talk about increasing potency, what does this mean in terms of the practical sense? How does this change how we handle the drug? Exactly. What this means is that the dose of the drug goes down. So same effect, less drug. This does not mean that milrinone works better than enamrinone. Enamrinone and milrinone have the same effect, but we can use less milrinone at a time. What this means too is that we can make a smaller pill, right? And that's the benefit of creating a drug that has higher potency. For someone who has swallowing issues, well, maybe the pill for milrinone is much, much, much smaller than enamrenone. In this case, they're IV only, so it doesn't uh, end up changing anything. I guess it's a smaller IV pill, exactly. Do we want me to review the mechanism? Does he go over mechanism really on the exams? I can't remember. Kind of, not really. Okay. All right. So, looking at the different drugs. Okay. Looking at the different drugs, we have the PDE3 inhibitors, which work internally, but we can also have the beta 1 agonist, which works externally, right? It connects to the beta 1 receptor, which is going to be GS, which also leads to an increase in CAMP, and that would be dobutamine. Big thing just to remember about dobutamine is that we have to have this norepi backbone. Right? And the other part that is really important is that right here in the alpha position, no alpha OH, this means that it's beta 1 selective. And that's really the two big factors there. I have in my notes that he gave nasideride. Did he give you guys nasideride? Yeah. Okay. Nasideride is a new drug. It's kind of an interesting molecule. Essentially, what it is, it is the recombinant version of natriuretic peptide. So if you remember when we talked about heart failure in Thera, BNP is a way of measuring the damage on the heart, right? And so the heart releases BNP. Heart releases BNP, natriuretic peptide, when fluid is high. And so what this does is that it tells the kidney to diurese. So the thinking behind nasideride is we just give the natriuretic peptide itself, and that's going to tell the drug, the kidneys to one, it tells the heart to slow down, right? Because the heart rate, the blood pressure is so high. So the two effects. One is tells heart to slow down. And tells kidney to diurese. That's really what it does. All right. Real quick, just to talk about these, can we give so just to put it this way, for our PDE3 inhibitors, the reason why we use these drugs IV only is not due to the structure. The structure would be absorbed. And I think if I check real quickly, the bioavailability of milrinone, 92%. So it has really, really, really good oral bioavailability. But why do we only really use it for IV only? Why would it be restricted to IV only? Yeah, there's some risk of arrhythmia, but in this case, we're using it more for an emergency situation. We're trying to reverse someone's heart failure quickly. And so we're going to administer it IV because of severe congestive heart failure. Same thing with dobutamine. It's the same sort of thing. We want to get it into their system quickly, so we're giving it by IV. That being said, because it mimics norepi so closely, dobutamine has a really short half-life. And that was something that we went over, I think, in exam 2. So just bear in mind that the dobutamine is given IV because we want to use it quickly, but also because it is metabolized so quickly. And then nesideride, because it's a recombinant protein, it can only be given IV. All right. The last one that we're going to look at is Entresto. Entresto is made up of two molecules. The first is valsartan, and the second is sacubitril. So sacubitril is interesting in where we have this dibenzo group. Sacubitril. Oh, I spelled it wrong. That's why. In sacubitril, we have this dibenzo group. Now, what's important to know about this is that this is highly metabolized, right? So sacubitril has this big lipophilic group that helps with getting the drug to the heart, but it also can be easily metabolized, right, through aromatic hydroxylation. Another thing that you'll notice about sacubitril is that we have this ester. So we know that it can be destroyed via esterase. So that the esters to help with absorption, knowing that it's going to be taken off, and then we're going to get a carboxylic acid here. Couple of other things just to talk about valsartan. Valsartan utilizes the tetrazole group. And what's interesting about these two drugs specifically, which is why I imagine that they were chosen, is that they both have that biphenyl group. That's really all there is. Yes. Yep. So it could go through aromatic hydroxylation as well. It can go through direct phase 2 through the carboxylic acid. It might even be able to do some aliphatic hydroxylation over here. All those different things. What's interesting about sacubitril is that it works by inhibiting the metabolism of the natriuretic peptide. So the nicitoride, the recombinant version, the synthetic version, if you gave them both, it would increase the effect of the nicitoride, which I don't think people end up getting both, but both are just extremely uh, expensive that nobody can get them. Yeah, no kidding. All right. Any questions on the heart failure drugs? All right. I'm going to skip over the anticoagulants and go into the eicosanoids, just because we could bang those out real quick. I have some pretty good tips and tricks for the eicosanoids that I remember. All right. For the eicosanoids, once again, we have to look at what the important molecules are and how they derive into the different molecules that we're talking about. So, first of all, just to remind people, first things that happens is that we start with icosanoic acid, icosanoic acid, which is metabolized into arachidonic acid, and it's from arachidonic acid that we get our three major groups of molecules. So we can have the prostaglandins, we can have our thromboxane, and in the other pathway, we can have our leukotrienes. Each one is going to be derived from the fact that this arachidonic acid has this funky little almost ring shape. And because of that, we're going to end up getting some pretty interesting chemistry coming out. So, in terms of the drugs, for prostaglandins, the way that I want you to think about them is they're essentially a cyclopentane with two chains. Depending on how those chains are formed, we end up getting all the different kinds of prostaglandins that we are used to. So, for example, actually, you know what I'm going to do? I am going to do it like this. Prostanoic. There we go. Did he talk about prostanoic? I hope he did, because it's the best way of looking at these different things. So for the prostaglandins, I actually want this smaller. There we go. For the prostaglandins, our PGE derived molecules. So the molecules that are going to be from PGE are all going to have a ketone here at the top of the molecule and an OH at the bottom. So the top chain has the ketone, the bottom chain has the OH. For PGF derived molecules, we have an OH at the top and an OH at the bottom. And then did he give you PGI or PGH? PGI? Okay. And then finally, for PGI, and I just want to make sure I'm not going to mess this up when I... Yes. For PGI, it is... Oh, I needed this for H. Prostacyclin backbone. Oops. There we go. And then for PGI, which is also known as prostacyclin, instead of that top chain being down and around, it is stuck in this furan moiety. And this is how we have our three different drugs. So when you're given a prostaglandin, the big thing to pay attention to is where that ketone is. Is it on the same chain that ends with a carboxylic acid, or is it not present in the molecule? He didn't give you PGD at all, right? PGD. Okay, all right. Does this make this process much easier, by the way? Okay, all right. That's the big thing. All right, so let's go through all the PGEs and we'll kind of break them down. The first one that we'll look at is alprostadil, misoprostol, and dinoprost. All of these are PGE derived. And the biggest thing here is that on misoprostol, the difference between these two molecules is that we've shifted up the OH a tiny bit, but really the big thing here is that we've added that methyl group. And so what is that going to do to our molecule here? How is that going to change our metabolism? Exactly. We're going to have less, actually in this case, no direct to and the reason is because that OH is too protected now. Steric hindrance, exactly. Now, this doesn't solve the big issue where we still have this, nice and exposed OH on both of them. We have this nice and exposed carboxylic acid. But when you compare alprostadil and misoprostol, we should expect misoprostol to have a longer half-life. Looking at dinoprost, we can see that it's PGF derived. And the big thing here is that the lack of the ketone is going to essentially mean that the PGF drugs are much more, what's it called? They are much more hydrophilic. They're way more hydrogen bonding. I think he wants you to just know what the drugs do and be able to like identify their class. So just to kind of give examples, because I imagine it's going to be something like, which of the following drugs is, going to do this? And it's all about, what does PGE do? So for our two drugs here, alprostadil and misoprostol, a couple of things that you might remember is that they have a vasodilatory effect, right? So this can have an effect in erectile dysfunction. This also has a big effect in pulmonary hypotension. They also have some smooth muscle relaxation. And this is the function that's used in cervical ripening in terms of things like inducing labor or in terms of things like abortion as well, where we want to make the cervix less tight in order for us to remove the fetus, or in terms of labor, make it easier for it to come out. In terms of dinoprost, really the only thing that we're using it for is the cervical ripening. Yeah, not a great word. All right. Did he give you when we talk about PGF drugs, so if he gives you a PGF drug, uh where PGE is all about smooth muscle relaxation, PGF is all about smooth muscle contraction. So these are your drugs like carboprost, latanoprost, travoprost. All of them are going to have that double OH backbone. And the big thing is we can use them in terms of like glaucoma. So that smooth muscle contraction is going to allow for the pressure to decrease. And then we can also use it in cases of postpartum hemorrhage, where what we are trying to do is we're trying to decrease blood flow to the area, not necessarily clot it, right? So what's going on after someone gives birth is that there is too much vascularization. And so in order to really see what's going on and find out where the bleeding is coming from, we would use something like carboprost in order to slow down the bleeding. Did he talk about leukotrienes at all? Maybe just to like identify them, maybe singular. Okay. In terms of our leukotrienes, oh, I should talk about thromboxane though. Therapeutically, it's useless, but it does play a role in the coagulation cascade. So, unlike the prostaglandins, which were a cyclopentane, thromboxane is a cyclohexane. The other important portion to this is that we have this bridging oxygen. And really, other than the bridging oxygen, we have a very, very similar structure, right? We have an OH kind of towards the bottom, and instead of having a ketone, we have the oxygen that's connected between carbon 2 and 4. Really, the only thing to know about thromboxane is that it's involved in the clotting cascade. We talked all about it the other day when we went through Thera. So it just facilitates platelet aggregation. That's that sort of thing. And then finally, for our leukotriene, because it is going through a completely different pathway, we are not going to end up having a similar shape to our molecule. So the leukotrienes, instead of keeping our arachidonic acid in this kind of cramped portion, it's going to rotate, and then we're going to add amino acid portions to it. So you can see that right here at the end of the other, at one of the double bonds, we add on this amino acid moiety to it, and that's what allows us to have the leukotrienes that go through lipoxygenase rather than the COX enzymes. And just really quickly, just to point them out, when we look at the different leukotriene inhibitors, things like montelukast and zafirlukast, what you can see is they're trying to mimic the structure of the leukotriene, but they're keeping the structure rigid by having all those double bonds in them. And that's really what we care about in this case, is that the leukotriene antagonists are being used to block this nice squiggly leukotriene from fitting into its receptor. So they have all these big bulky groups associated with them. That's all we really care about. All right. Let's head back and let's do anticoagulants, and we'll round it off with our NSAIDs. because by then we will have touched on all the good stuff. What day is the MedChem exam as well? Thursday? Okay. So it goes PCOL on Monday. No. Druglet, PCOL, MedChem Thera. Oh, okay. So Tuesday, Wednesday, Thursday for the classes that I tutor. Okay. Tuesday, Thursday, Friday. Okay. Oh, so we have a gap we have an extra day for MedChem then. Oh, okay, great. Great. Good to know. All right. Let us talk about anticoagulants and all that good stuff. Yesterday when we talked about the anticoagulants, Thursday, one of the things that we talked about how is that there's lots of different molecules that have very, very similar function, and that's because they're all in one way or another, they are a synthetic version or not. So for example, the natural molecule heparin, this is what we have in our body. It's what's found in, lots and lots of different animals. And essentially what heparin is just a bunch of cross-linking sugar molecules. So the way that I'm not going to go into it specifically because I talked all about it when we went through Thera, but the key features here, does heparin taste good? It would start, I don't know. I don't think it would. I think it would taste bitter. I almost said that it would break down your tongue. Why do all sugars taste bad? Well, starch tastes bad. It's not until you break it down with the sugar enzymes in your mouth that, bread tastes good. So we have a bunch of polysaccharide structures. And what this is going to do is that it's going to make it extremely water soluble, right? Extremely hydrophilic. And so the ability for heparin to go through the blood is reliant on the fact that it has this two this very, very water soluble nature to it, right? So in order for it to get to the clot, it needs to be able to go through the water to do it. There's two really big key components to it. First is we have the glucuronic acid. So we have the glucuronic acid component. And you can identify the glucuronic acid because we can see that we have that COO minus, or sometimes it might be written as COOH, right? And so you can see that we have another glucuronic acid moiety right here. What is connected to every glucuronic acid is this glucosamine. And so what you end up getting is a disaccharide stuck together, where we have the glucosamine bonded to the glucuronic acid. couple of important points. Can you have an oral form of heparin? Not at all, right? Extremely water soluble. So this means that it's going to be IV only, right? It's also going to be used in pretty much emergency situations. So again, we want it to interact with that. What do you notice about the charge of heparin? What charge is heparin? Extremely negative, right? We have all this negative carboxylic acids. We have these negative sulfate groups, sulfonyl groups. We have negative glucosamine groups. And so the reversal agent is going to be protamine sulfate. If we look at the structure of protamine sulfate, uh, da, da, da. Da, da, da. I can't get a good structure of it. I guess I'll have to go with this. What is in protamine is essentially a wheelie looking peptide where we have a lot of functional groups that have NH2 plus in them. So things like lysine or the arginine. And what this is going to do is it's going to attract and wind its way around the heparin and prevent it from acting. So the reversal agent for heparin is protamine sulfate because this is a positive ion attracting the negative heparin. Here's a good example of that. So we have, in this case, it's talking about DNA, but the protamine is revolving around the negative structure. When we go on to our next batch of drugs, the low molecular weight heparins, instead of using this unfractionated heparin, meaning that we're using all of the heparin that's available, what we're doing is we're taking natural heparin and we're spinning it and only taking a portion of what's left over. So instead of having, hundreds of these polysaccharides connected to each other, what we're left with is only maybe a few of the polysaccharides in a row. And so there we go. Now, what's still really important to bear in mind is that we still have the disaccharide of the glucuronic acid and the glucosamine. That is still a needed function of it. But what we've done is that we've decreased the molecular weight of the molecule. What this does is it changes the functionality a little bit. So instead of it working on um, antithrombin 3 in the same way that heparin does, it works in a kind of slightly different way, which I talked about with Thera the other day. But what do we think the reversal agent is going to be? Do we think the reversal agent for low molecular weight is going to be the same, protamine sulfate, or should it be something different? Yeah, it's the same drug. Why? Because low molecular weight heparins like enoxaparin, dalteparin, they're all the same. It's the same structure. We're just using strands that are smaller. And because of that, it means that we have uh, essentially the same molecule. What's important to note here is that we only get a partial blockade or a partial reversal. And the reason for that is because it's smaller, right? So you'd have to use a lot more protamine sulfate to mop up all of this, uh, you know, uh, smaller strings of heparin, right? Think of it if you're using a vacuum cleaner to pick up string. It's easier to pick up long strands of string with a vacuum than it is to pick up, very, very tiny pieces of string, right? The one that is similar to this that we should talk about is fondaparinux. Did he give that to you guys as a? He did? Okay. Fondaparinux. Okay. For fondaparinux, in in the same way that low molecular weight heparin is where we spun it to get, more specific lengths of heparin, what fondaparinux is just synthetic heparin. What that means is that it's going to work very, very similar to heparin and low molecular weight heparin, but the difference is that we can control the length. And what you'll see is that we hit the same thing. Here we have the glucosamine. Uh, shoop, that crazy? Yeah, here it is. We have our glucosamine group, and here we have the glucuronic acid. The difference here is that fondaparinux is a pentasaccharide, always. It is always going to be a pentasaccharide. So whereas heparin can be huge in its length, hundreds and hundreds of uh, sugar molecules stuck together, low molecular weight heparin like enoxaparin maybe, tens, 20, 30 put together. Synthetic heparin like fondaparinux is always going to be five uh, pentasaccharides stuck together. All right. Moving right along. In a different class, we have warfarin. Warfarin has a ton of things wrong with it. It is uh, a, a narrow therapeutic index drug. You have to be really, really careful with how someone is taking their heparin, as well as the things that happen around it. What's important to note about heparin is that it is mimicking the structure of vitamin K. Uh, why can't I get like a good... all right, I'll go with this. Vitamin K is utilized in the body as a way to make certain clotting factors. And it's primarily being used in order to act as a cofactor where it gets oxidized and then reduced in this cyclical way. And the result is that we can keep utilizing vitamin K in a way where we can have clotting factors be made the way that they're supposed to. What warfarin does is that it mimics certain pieces of vitamin K in a way where it can fit into the enzyme, but then it doesn't leave. There are lots of different what are called coumarins, which is the functional class that warfarin is derived from. But really, what they're all going to do is relying on this uh, this functional group right here. Oop. This OH group is an acidic group which undergoes something called tautomerization, which means that it can switch between being an OH and a ketone. Yeah, for those who tutor with me, this is an enol. The big thing here is that because of that ability for it to switch back and forth, it is more easily able to kind of fit inside of the enzyme and disrupt what it's supposed to do. There are a couple of key facts about that we should talk about. In terms of absorption, we have high absorption. I think it's as high as like 100%. And the reason is because if you look, other than that OH, which can tautomerize into a ketone, we don't really have any hydrophilic groups. So we have very, very, very high absorption. Likewise, we also have very, very high protein binding. So the distribution of warfarin is much, much higher than other drugs that have a similar structure. Because of all of those benzene rings and this OH, we have lots and lots of sites of aromatic hydroxylation. And that's primarily the way that we're going to be metabolizing warfarin. And normally that wouldn't be a bad thing, right? Lots of drugs can undergo aromatic hydroxylation. The problem is that warfarin has a very narrow therapeutic index. So the fact that it's narrow, as well as utilizing a very common pathway, means that we have a high chance of drug interactions. And then finally, in terms of excretion, because of the aromatic hydroxylation, we're going to end up with an OH here, and pretty much it's going to be removed from the body via glucuronidation and then through the urine. Great question. Why doesn't it go through with the lactone? if I had to guess, I'd imagine it has to do with this double bond in the enol function, kind of stealing away some of the electron density. It can be metabolized through an esterase. I just think that in terms of what is the easier pathway for the body, it goes through aromatic hydroxylation. Would it be wrong for you to put esterase? No, it would be possible. For whatever reason, it just doesn't really undergo it. What's important to know, and I talked about this in the Thera video, is that each one of these is a source of drug interactions. So warfarin has tons and tons and tons of ability of drug interactions, lots of different ways that it ends up interacting with other drugs, with your diet, with tons of terrible, terrible things. So the uh, the big thing here to kind of bear in mind is just that it's how do I want to put this? Um, you have to be really careful with warfarin. That's really what it comes down to. All right. I believe our last sort of drugs that we are going to be talking about is it's a So in terms of the PD3 inhibitors, what was he talking about again
So,
before?
so it was a little weird. Um, you kind of went on a tangent, and he was like, "Oh, so can you tell me why we don't use anagrelide and the other drug for things like, um, I think it wasn't arrhythmia, it was heart failure." And no one could answer him because none of us knew. And he went on a tangent about camp and CGMP and how it's too strong, and none of it made sense. So if you happen to know why something like anagrelide isn't used for heart failure, that would be lovely input. But if you don't, then I can try and find him.
I think I know what he's talking about. Um, the let me think real quick. Because anagrelide is it's a PDE3 inhibitor, right? Am I crazy?
I think so. We have it as just a PDE or PDE inhibitor. He didn't specify three for us for some reason for those. I don't know why.
If I had to guess, well, so this is what I can say is that when we look at the function of uh, in terms of platelets. So, how do I want to explain this? When we have a blood vessel injury, I think I know what he was talking about. But essentially what it is that when we have a blood vessel injury, such as, you are trying to cut up some watermelon, you accidentally cut yourself. What ends up happening is we have our blood vessel up here, and below the blood vessel is our smooth muscle. And that's what controls the vasoconstriction, vasodilation. And inside the smooth muscle is all of these collagen fibers. If you remember from Pico with the mechanism of how the white thrombus or the initial clotting happens, essentially what goes on is that first in the blood vessel, we have our von Willebrand factor, which is like little drops of glue. And the von Willebrand factor is going to stick to the collagen, and that's going to enable a platelet to come in and stick to the collagen. When this initial platelet is able to bind to the von Willebrand factor, what it does is it transforms from its unactivated into its activated shape, which is all spiky and it kind of looks like a foosball. What this activated platelet is going to do, in order for it to attract other platelets and to get it to bind, it's going to release a couple of different compounds. The I just want to bring up the diagram. I don't get the things wrong, so people don't yell at me. They're always yelling. Mm-mm-mm. Yeah. What ends up happening here is that that in order for other platelets to be attracted to the platelet that managed to stick to the von Willebrand factor, what it's going to do is it's going to release a couple of different molecules that will activate our other platelets. One of those molecules is ADP, adenosine diphosphate. What ends up happening here is that ADP will find another platelet that's floating by and bind to the P2Y12 receptor. P2Y12 receptor. So ADP is going to sneak in, and the ultimate result of this is it's going to activate this platelet to also be ready to form the clot. Is this making sense so far? Okay. All right. Sweet. What happens on a molecular level is that we end up having that P2Y12 section. And I just want to make, yes. So we have our P2, oh, wrong color. P2Y12 receptor. And that's waiting for ADP to come in and bind to it. P2Y12 is a GQ linked molecule. GQ linked receptor, I should say, which is going to go through all the different stages that we've talked about, where it's going to go through PLC, which is going to create PIP2 and DAG. So we have IP3 and we have DAG. Oop, am I crazy? Sorry, let me just check one thing. Nope, my bad. It's GS. You're thinking of something very close. And I will explain where you're thinking of GI in just a second. My bad. It's GS. So this is going to go through GS, which means that we're going to go through adenylate cyclase. And what this is going to do, oh, it might be P2Y1. That might be it. I think, yeah, might be P2Y1. What this is going to do, adenylate cyclase, is convert our CAMP into, ATP into cyclic AMP. Hopefully this should be familiar by now. What you guys remember is that what ends up happening is that PDE is responsible for breaking down CAMP into 5-AMP. So in terms of giving a drug like anagrelide or these other PDE3 inhibitors like dipyridamole or silostazole, what they're doing is that they're preventing the breakdown of CAMP uh, uh, enabling for how do I want to put this? Breakdown of CAMP, which eventually leads to more. You're I'm getting confused. All right, give me 1 second. P2Y1 is increase in CAMP, pKa, AMP, blocking that, raise CAMP. Okay. Now I figured out where I was going. What this is going to end up doing is that once we raise CAMP levels, raising CAMP levels leads to less platelet activation. This is where I was missing it. P2Y1 is GQ, P2Y12 is GI. I think I'm going to have to go back and I'm going to have to look at this again because I don't remember this at all. Because this is getting into Vorapaxar, which is always a slippery slope. we'll come back to this probably tomorrow if you remind me. All right, let's go back to the drugs. I think that might be a better way to kind of handle this. When we go to what the P2Y12 receptor blockers are, this is where we talk about all the GRELs. So P2Y12, where ADP is binding to, all of our GRELs. What these guys are mostly what they're mostly relying on is a sulfur in order to make irreversible bonds with the receptor. So in terms of prasugrel and clopidogrel, it's this sulfur moiety down here that we're really relying on. So the sulfur is going to be creating cross links with the receptor, and that's what's going to prevent it from allowing the receptor to be activated subsequently. So without that sulfur moiety in it, we wouldn't have any ability to have the drugs act the way that we want. The important point here is that clopidogrel and prasugrel are prodrugs. The reason is because what's going to happen to them is they're going to be metabolized in a way where we're going to free that sulfur and enable it to bond better. So, for example, in the case of clopidogrel, in order for it to do what we want, we need to get this sulfur to be taken out of the ring. How it does that is it goes through one of the enzymes, and that enzyme is going to enable us to break the ring. And that's going to create a SH group, the thiol group. And it's that thiol group that is going to work with the receptor, which has its own thiol group. And this creates that disulfide link which inactivates the receptor. So clopidogrel isn't necessarily a prodrug because it has an ester. It's a prodrug because we're relying on the body to cut open this cyclopentyl group, if that makes sense. Any questions about that? Do we want a different picture? I can grab a different picture. There might be a better picture where you can see it. So here you can see that the enzyme has cut open the ring, and now we have that free SH group that we need. Kind of interesting. When we look at the other drug that's in the same class, ticagrelor, what we notice is that ticagrelor also has that sulfur group. So it's still a prodrug. But the difference here is that the bioactivation by the body is much, much, much easier, right? Yes, same with prasugrel. Prasugrel needs to be released by the body as well. So this is a prodrug. So all of the drugs in this class are prodrugs because we need the body to, in this case, remove this propyl group, or in the case of prasugrel and clopidogrel, we needed to unhook this ring. The difference between them is that where clopidogrel is irreversible, prasugrel is irreversible, ticagrelor is reversible. And just to bring them down real quick, just so that we can compare them. When we look at the difference between them, so I'm just going to make it look like how it would after its metabolism. What's the main difference between the ticagrelor sulfur and the clopidogrel sulfur? So let me just erase out the portion that gets removed. What's the main difference between these? Exactly. In ticagrelor, our SH is bonded directly to an aromatic ring, all those double bonds. And this is what is enabling ticagrelor to be reversible, versus clopidogrel has a sulfur that is not on an aromatic ring. And that's why clopidogrel and prasugrel are irreversible. They have tighter bonding sulfurs compared to ticagrelor. All right. The last group that we are going to look at tonight, and then we'll have to do NSAIDs a different day, is yeah, we'll talk about the PDEs tomorrow, just so that way I can look up what that thing was talking about. Maybe it would be better. Let's wrap up here, actually. That might be better. And then tomorrow we'll kind of finish up on this MedChem stuff, and then we'll do practice, 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 practice. We'll just keep practicing. And I'll put up a poll on what people want to practice on. All right, so we'll wrap up here.